Hi, thanks for joining me today. I've got a fun geometry problem for you. We want to know, is it possible to cover the Euclidean plane with discs of radius at least 5, such that the interiors of no two discs overlap and each integer point is covered? So we have the real plane, or the Euclidean plane, like so, and we draw on all the integer points. So that's the points with both coordinates are integers. Okay, so it goes over the negatives as well, and so on. And we want to know, is it possible to draw on these discs, and each disc has a radius at least 5, onto the plane, say something like that, and so on, across the whole plane, such that every single integer point is covered. If you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to jump straight into the solution. Okay, so the solution to this problem is in fact no. It is impossible to cover the plane with these discs such that every integer point is covered. And the way we're going to do that, or the way we're going to prove that, is by contradiction. So suppose for contradiction this kind of covering exists. Well, let's draw it on and let's zoom in on a particular area. So let's say we have this disc here, being one of our discs of radius at least 5, this guy here, maybe one over here, and one over here, like so. Okay, so I've zoomed in on our kind of covering, and what I've done is I've kind of have a little region here, and this region here we know does not contain an integer point because these discs here cover every single integer point, or at least that's what we're assuming. Next thing we're going to do is look at this kind of undisked region and then draw on a small dotted disc. So let's say this guy here, like so. And what we want to do is make this dotted disc as big as possible. And it's very clear that it's not as big as possible just yet. We can just stretch it a little bit and keep it not, overlapping with any of these discs, but it's also be bigger than the one I've currently drawn. So let's make it a bit bigger, like so. Something like that. And then hold on, we can actually make it a bit bigger. So it's tangent to this circle at the moment, but if we allow it to be tangent to another circle, we can make it even bigger. So let's get rid of this circle and make an even bigger one. So we get something like that. Okay, that's supposed to be a circle. Okay, and then we go, hold on, this still isn't of maximum size because we can shift it about maybe this way a bit or this way a bit and make it even bigger. So let's get rid of this guy here. Okay, and it's going to be even bigger. So it's going to look something like that. Okay, so we've drawn this dotted disc on, it's a maximal size, and kind of by this argument that I've just kind of provided by drawing a few different dotted circles, we know that this big dotted circle is going to be tangent to at least 3 of these big discs here with radius at least 5. Next thing you want to do is just consider the center of these discs and the center of this dotted disc that I've added. Okay, and let's call the radius of this disc here r, and let's add on these lines here from the centers of the big discs to the dotted disc, like so. Now the angles around this point here, of course, are just going to add up to 360 degrees, so by a very simple pigeonhole argument, we know that at least one of these angles here will be of size at most 120 degrees, because of course if each of these angles here were strictly bigger than 120 degrees, then the sum would be strictly bigger than 360 degrees, which is impossible. So we're going to choose the angle which is smallest, so it looks like it's this one here, and we'll call that angle theta, and we know that theta is, between 0, so strictly bigger than 0, and at most 120 degrees, like so. So theta is this guy here. We're going to call this circle here A, this circle here B, and we'll call the radius, this guy here, is going to be little b, the radius of this guy here is little a, this guy here, this length here is just going to be d, and one thing we notice about d is it must be at least a plus b. So d is bigger than or equal to a plus b, because we know these two circles don't overlap. And we also have this angle theta here. So notice that this side length here of this triangle, so if we consider this triangle here, this side length is b plus r, this side length here is a plus r, and this side length here is d, where d is at least a plus b. Now what we want to do is use the cosine rule on this guy here, noting that theta is between 0, 100 and 120 degrees, and then derive an inequality involving a, b, and r. Let me clean up the whiteboard, and we'll do that. Okay, so I've just drawn up the triangle we had on the side here, and I've gotten rid of all the big, large discs, And as I said, what we're going to do is just use the cosine rule on this triangle here. So we're going to get d squared is equal to the sum of the squares of the other two side lengths, so a plus r squared plus b plus r squared minus 2 times the side lengths a plus r, b plus r, and then cosine of theta. Just squeeze that in there. So this is an equality just by the cosine rule. And now cosine of theta, remember theta is at most 120 degrees, so if we draw it on, we just think about what cosine theta looks like. That's 90, and that there is 120. Cosine of 120 degrees is minus a half. So cosine of theta, because theta is obviously non-negative, cosine of theta is going to be somewhere between minus a half and 1. So if we think about this thing here, this thing, because we've got a minus 2 up front, is going to be somewhere between minus 2 and positive a half. So, positive 1, because we're multiplying the negative half by negative 2. So this minus 2 cos theta is going to be somewhere between minus 2 and positive 1. So in particular, it's going to be less than or equal to kind of the maximal case where cosine of theta times minus 2 is positive 1. So this is less than or equal to a plus r squared plus b plus r squared plus a plus r b plus r, like so. But remember, d is bigger than or equal to a plus b, so we know that d squared is going to be bigger than or equal to a plus b squared, so that we have that a plus b squared is going to be less than or equal to this guy here. So a plus r squared plus b plus r squared plus a plus r times b plus r, like so. Now if we just go ahead and expand all this out and then cancel and collect like terms, we're going to get the inequality ab is less than or equal to 3 times a plus b times r plus 3 lots of r squared. So I'm not going to go from that step to that step, it just involves expanding each of these brackets here, and as I said, cancelling and collecting like terms, but you're going to get from this line to this line here. And now I claim that this is going to lead us to a contradiction. Anyway, let me clean up the whiteboard first. Okay, so we just derived the inequality AB is less than or equal to 3 times a plus b times r plus 3r squared. Now we can actually find a nice bound on r if you recall how we constructed it. Remember, r was the radius of the kind of dotted disk that we added, and this dotted disk was kind of in the unshaded region, which in particular did not contain any integer point. So that means this circle, this kind of dotted disk, it can't be that big, because if it was big it would have to cover one of many integer points. So that means that we can find a bound on r. Now if we just consider kind of a unit square, like so, so it's got side lengths 1 and each of the corners here are just integer points. And essentially what we want to do is add a circle onto that, which is pretty big but doesn't cover any integer points. Well, we can think of a circle which just misses this corner, just misses this corner, just misses this corner, and just misses that corner. And then we ask ourselves, well, what is the radius of that disk there? Well, if we just put the centre of the square there, we see that the radius has to be less than the diagonal length of the square. And well, what is the diagonal length? Well, we know that this guy here is a half, this guy here is a half, so just by simple Pythagoras, that diagonal there must be 1 over root 2. So we must have that little r is strictly less than 1 over root 2, like so. Now, let's go back to this inequality here, which you've already derived. Let's rearrange it. So we get 3r squared is bigger than or equal to AB minus, what am I on about? Let's get rid of this. AB minus 3ar minus 3br, like so. So just bring this guy onto this side here. But then this thing here is simply a minus 3r times b minus 3r minus 9r squared. Okay, so let's just check that. A times b gives us the AB there. A times minus 3r there. B times minus 3r gives us that. But then of course we've got minus 3r times minus 3r, which is plus 9r squared. So we've got to subtract it off like so from this side. But then just adding the 9r squared onto both sides gives us that this thing here holds. So 12r squared is bigger than or equal to this guy here. But remember what A and B were. They were radii of these disks, and we know by the assumption that A and B therefore must be at least 5. So this guy here is bigger than or equal to 5 minus 3r squared. Okay, because this thing here is at least 5 minus 3r, as is this thing here, at least 5 minus 3r. So if 12r squared is bigger than or equal to 5 minus 3r squared. So 5 minus 3r squared is less than or equal to 12r squared, but we just had that r is less than 1 over root 2. So that means r squared is going to be less than 1 over 2. So multiply both sides by 12. 12r squared is going to be strictly less than 6. So 5 minus 3r squared is less than or equal to 12r squared, which is strictly less than 6. But I claim that this doesn't hold, because if we just rearrange this, so we can take the square root of both sides. So 5 minus 3r is less than root 6. And notice that I don't have to worry about minuses or anything like that, because r is very small. It's less than 1 over root 2. So this thing here, 5 minus 3r is positive, so I don't need to worry about putting a minus sign here or anything like that. So 3r is, so I've got 5 minus 3r, and that's going to be at least 5 minus 3 over root 2, and you can just check that that is positive. So 5 minus 3r is strictly less than root 6, so that's going to tell us that r, or 3r, is bigger than 5 minus root 6, and then that means that r is bigger than 5 minus root 6 over 3, but we know that r is at most 1 over root 2, like so. So in theory we should have that 1 over root 2 is strictly bigger than 5 minus root 6 over 3, but as you'll see in just a second, this is not true. Okay, so we just said that 1 over root 2 is bigger than 5 minus root 6 over 3, and we want to show that this leads to a contradiction. And I've written up a little number here, r equals 3 plus 2 root 3 over root 2. We're going to get onto why I've written that there in just a second. Anyway, let's try and derive a contradiction from this. Let's multiply both sides by 3 root 2, so we get that 3 is bigger than 5 root 2 minus 2 root 3, because root 6 times root 2 is root 12, and we can take out a root 4 from that to give us 2 root 3. Let's bring on the 2 root 3 onto this side, so we get 3 plus 2 root 3 is bigger than 5 root 2, and then square both sides. On this left hand side we're going to get 9 plus 12 root 3 plus 12. Okay, so 3 squared is 9, 3 times 2 times 2 times root 3 is going to be 12 root 3, and then 2 root 3 or squared is just 4 times 3, which is 12, and that's supposedly bigger than 5 root 2 squared, which is 25 times 2, so 50. Okay, well, rearranging this, bring the 9 and 12 onto that side there, we get 12 root 3 is supposedly bigger than 29, but 12 root 3, well, we know that that thing there is going to be strictly less than 12 times root 4, and root 4 is just 2, so 12 times 2, which is 24. So we get that 24 is supposedly bigger than 29, and of course that is not true, and we've arrived at our contradiction. And if you had a calculator, I guess you could have just plugged it in there, but as a pure mathematician we try and stay away from calculators where possible, so we get 24 is bigger than 29, and that of course is a contradiction. Anyway, that solves the problem. We cannot cover the entire plane with these discs of radius at least 5, such that every single integer point is covered. And in fact we can use the exact same argument, but instead use this number here, and this number here is less than 5, okay? And if we plug it, so i.e. if we have each circle, each disc being radius at least this number here, then using the exact same argument we'd also arrive at a contradiction. So we can't use discs of radius at least this guy here. Okay, so, and as I said, this is less than 5. So we can make the argument a little bit more tight if we wanted to. Anyway, that is all for this video. I hope you have enjoyed it. Thank you for watching. I'll catch you in the next one. Have a great day.